Hi, thanks for joining me. Today I'm going to be doing something slightly different. I'm going to be sharing what I believe is a really beautiful theorem all to do with Sudokus. So if you don't know how Sudoku works, let me quickly explain. But if you do know how Sudoku works, skip ahead a little bit. I'll leave a little timestamp on screen for where you can skip ahead to. And until then, I'm just going to explain the basic rules of Sudoku. So a Sudoku is this 9x9 cell grid. So we've got 9 cells. These small squares here are called cells. Ignore the colours on the grid for now. But these 9x9 cells, these small squares here are called cells, and we've got 9 across the bottom, 9 across the top, so we've got a total of 81. So those are called cells, and these sort of 3x3 cell boxes are known as boxes. So we've got 9 of these boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9 on the grid, and of course we've got 9 rows all the way down, and then 9 columns all the way across. And the aim of a Sudoku is to fill in each cell with a unique digit 1 through 9, so that each box, row and column contains each of the digits 1 through 9, each occurring exactly once. Okay, so you're given a few digits already, like I've drawn on this sort of example Sudoku, and from that you want to deduce where all the other digits in the grid go. So for example, in this box here, we know we need to have the number 8 somewhere, and it can't go in any of these 3 cells, because we already have an 8 in that column, and then that would repeat an 8, and we're not allowed to do that. Similarly, we can't have an 8 in any of these 3 cells, because there's already an 8 in that row, and again, if we were to put an 8 in any of those 3, that would repeat the 8 in that row. And finally, we can't put an 8 in any of these 2 cells, because there's already an 8 there in that column, and we can't put an 8 with the 6, because each cell has its own digit in, so the only place we can place an 8 is there. Okay, and we use logic like this to go ahead and fill in the whole grid. So that's the basics of how a Sudoku works, and I'd recommend Sudokus as a fun logic puzzle for you to try. It's something just to keep you occupied. You'll generally find them in newspapers and whatnot. Anyway, let's move on to what I'm doing in today's video. I'm going to be showing you what is called the Phistomefel Ring Theorem. Now this actually comes from, or at least I found this off another YouTube channel called Cracking the Cryptic. They make loads of sort of Sudoku videos. This isn't a promotion for them, but I really do enjoy their channel, and I'm sure a lot of you will as well. So I'll leave a link to their channel in the description below. That's where I got this theorem from, and it's named after a Sudoku sort of creator and solver who goes by Phistomefel, who once submitted a problem which uses this ring theorem to solve. So what is this ring theorem which I claim is so beautiful? Well, here's just an example Sudoku grid with these numbers on, but you can see I've coloured in some cells in green. So these 4 cells, these 4 cells, these 4 cells, and these 4 cells. So that's 16 different cells in green. And you'll notice that there are also 16 cells in red, forming this ring around the central box. Okay, so you've got 4 there, that's 8, 9, 10, 11, 12, 5 there, that's 10, I can't count today, that's 10, 11, 12, 13, 14, 15, 16. So 16 red cells. Can you guess what I'm about to claim? I claim that the green cells equal the red cells. So if we were to write out the digits that go into the 16 green cells, we get a list of 16 numbers. And I claim that if we did the same for red, so write out the list of numbers that fall into the red cells, we'd also get 16 numbers, and those lists will be identical, obviously up to some rearrangement. So if there are 3 2s in this ring, then that means in the list of the 16 green numbers, we must have 3 2s, and so on for every other digit. That is this beautiful ring theorem. Now obviously, or maybe it's not particularly clear why that's true, but that's what we're going to be solving in today's video, or proving in today's video. Proving that the list of 16 red numbers equals the list of 16 green numbers. Let's get stuck into the proof. Okay, so what I've done is I've removed all the digits from the grid, because in fact this Phistomefel ring theorem applies to absolutely every single Sudoku grid, and it also includes sort of Sudoku variants which hold the same basic rules of Sudoku, so for example killer Sudokus as well. Anyway, what I've also done is I've introduced some new colours and changed things about. So what we had before was this ring being all in red, and now all I've done is I've just changed the corners of the ring into blue, like so. What we want to do is show that the ring, which is now red plus blue, we want to show that red plus blue equals green. So the list of 16 numbers which we get when we write out all the reds and all the blues should be equal to the list of 16 numbers we get when we write down all 16 greens. That's the claim at least. And I've also introduced these black colours here, sort of to fill up these boxes here. Now what we're going to do is sort of show two sort of sets are the same and then look at the colours that correspond to those sets. Okay, so firstly let's consider each of the corner boxes like so. Well, when we sort of look at all those digits together, we're going to get 4 sets of the digits 1 through 9 because each box has the set of digits 1 through 9 in a complete solution. So in the complete solution, this will have one lot of the digits 1 through 9, another lot of the digits 1 through 9, another and another. So 4 lots of the digits 1 through 9. So I'm going to denote that like so. Like so. But what does that equal in terms of colours? Well, that's all of the greens plus all of the blacks plus all of the blues. Okay, so 4 lots of the digits 1 through 9 is the same as the greens plus the blacks plus the blues. Like, oopsie daisy, like so. Cool. So we've shown that 4 lots of the digits 1 through 9 is just green plus black plus blue. However, we can now look at the columns and the rows of this grid. So now if we focus on column 3, column 7, row 3 and row 7, and we're going to do a similar thing and look at the list of numbers there. Well, if we look at column 3, column 7, row 3, row 7, when we look at all of those numbers, we're going to include all of the blacks. So we're going to get black. We're also going to get blue, so plus blue. Okay, because when we look at this column, we're going to get these 2 blues, this column we're going to get these 2 blues. But notice when we look at this row again, we're going to double count the blues. And when we look at this row again, we're going to double count the blues. So we'll take that into consideration in just a second. And when we look at these rows, we get these reds. When we look at these columns, we get these reds. And when we look at these rows, we get these reds. So we're also considering reds. Okay, and again, this is going to equal 4 sets of the digits 1 through 9. Well, why is that? Well, that's because this column contains each digit 1 through 9. This column contains each digit 1 through 9. This row contains each digit 1 through 9. And this row contains each digit 1 through 9. So 4 lots of the digits 1 through 9. However, remember I said we have to consider the double counting of the blues. So when we do this, we get 4 lots of the digits 1 through 9, but we've double counted the blues, so we have to subtract off each blue. So we're subtracting off a blue. Okay, so what does that tell us? Well, that tells us that black plus, if we add sort of blue to both sides, we get that black plus 2 blue plus red equals 4 lots of the digit 1 through 9. Wonderful. Now we've got 2 expressions for 4 digits, 4 sets of the digits 1 through 9. We've got green plus black plus blue equals black plus 2 blue plus red. So if we just compare them now, we get that this guy here, let me just make sure my colours are intact, equals this thing here equals this thing here. But then of course we can cancel the blacks and we can cancel 1 lot of the blues, and then we're left with green equals blue plus red, like so. So a lot of different colours being used today. So green equals blue plus red, and that is exactly what we wanted to show, because green are these 16 squares here, blue are these 1, 2, 3, 4 squares here, and red are the rest of the ring, like so. So if we went back to our original drawing where this whole ring was just red, we'd get that red equals green, and that's what we wanted to show. And I think this is beautiful because you can use, if you know what these digits around the ring are, you can work out what digits these greens are. You won't know the order, of course, but you'll know that you'll have to see, if you see 3 2s around this ring, you've got to see 3 2s in these greens. And also vice versa. If you know the digits in the greens, you can then use that to help you work out the digits in this ring, like so. And I think that this is a beautiful theorem. And using this idea of equating sets, you can also build, like, sort of show other sort of regions of the graph, regions of the grid, are equal to other regions of the grid. But this, I think, is the most beautiful because it's really symmetric and it forms this really nice ring around the central box. Okay, I'll leave a link in the description below to a Cracking the Cryptic video, which you can use this theorem to help you solve that Sudoku. But yeah, I really hope you've enjoyed this theorem. This is one of the most beautiful theorems I've seen before, let alone just in Sudokus. But I mean, I don't really know how many theorems there are in Sudokus. I think this is really, really beautiful and doesn't use that much maths, and it doesn't use anything too, you don't need to know any calculus, you don't need to know any geometry. You just need to understand when two things are equal, and you get this really beautiful ring around the central Sudoku box, equaling the corners of the Sudoku box, Sudoku grid, sorry. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.